Now, I will go to the next question. A fully charged capacitor has a capacitance C. It is discharged through a small coil of resistance wire embedded in a thermally insulated block of a specific heat capacity S and mass M. If the temperature of the block is raised by delta T, the potential difference V across the capacitance is option number 1, square root of 2 MC delta T divided by S. Second one, MC delta T divided by S. Third one, MS delta T divided by C. Fourth, square root of 2 times M into S into delta T divided by C. You are all aware that if a capacitor of the capacity C is charged to a potential difference V, the energy stored in a condenser is half of C multiplied by V square. If it is connected to a resistor, entire energy stored in the condenser will discharge through the resistor. It is given that the resistor is kept in thermally insulated block. That means heat produced in the resistor is not dissipated out, or in other words, it is not radiated out, and therefore entire energy is utilized in heating the wire. Therefore, the energy discharged by the condenser must be equal to heat energy required to raise the temperature of a wire of mass M and specific heat capacity S through a temperature difference equal to delta T. And you know by heat that it must be equal to M into S multiplied by delta T. Making V the subject of the formula, V is equal to, since it is V square, it will become under root of 2 will come to the other side in the numerator, 2 times M into S multiplied by delta T whole divided by C whole divided by C. Therefore, option D is the correct answer. There is another very important concept in static electricity which is very useful in CET examinations, and that concept is, I request you to be attentive to hear it. If two capacitors of the capacities C1 and C2 are charged respectively to the potentials V1 and V2, if they are connected in parallel, then common potential difference across the combination is given by V is equal to C1 V1 plus C2 V2 divided by C1 plus C2. This example is absolutely dependent on this particular concept. Let me read the question then. A 10 microfarad capacitor is charged to a potential difference of 50 volt and is connected to another uncharged capacitor in parallel. Now, the common potential difference becomes 20 volt. The capacitance of the second capacitor is option number A 10 microfarad, option number B 20 microfarad, option number C 30 microfarad, option number D 15 microfarad. Just now, before reading the question, I told that if there are two capacitors C1 and C2, if they are respectively charged to the potentials V1 and V2, and if they are connected in parallel, then the common potential difference is given by V is equal to C1 V1 plus C2 V2 whole divided by C1 plus C2. Note that the second capacitor is uncharged. If it is uncharged, potential across it, that is V2, must be 0. You may note that common potential is 20 volt, C1 is equal to 10, V1 is equal to 50, C2 is not known, V2 is equal to 0. V2 is 0 because second capacitor is uncharged. When it is not charged, there cannot be any potential difference. Hence, substituting the values, V is equal to 20. This is equal to C1 V1. C1 is 10, V1 is equal to 50 plus, since V2 is 0, second term is 0, divided by C1 is 10 plus, I do not know the value of C2. This should be calculated. Possibly, you may be having one doubt in your mind that the capacities are given in microfarad and I have eliminated it. Remember, 10 raised to minus 6 is common both in numerator as well as in denominator. Therefore, 10 raised to minus 6 gets cancelled. On account of that reason, there is no need for you to take 10 raised to minus 6. Then, cross multiplying, you have this as 10 plus C2 is equal to, I will take 10 plus C2 over here. If I bring 20 to RHS, 500 divided by 20 is going to be equal to 25. One can easily notice that C2 is equal to 25 minus 10, that is equal to 15 microfarad. Therefore, option number D, that is 15 microfarad, is the right answer.